Yes. Okay, I will briefly go through this lecture. Okay. We were discussing about cofactors, Shannon expansion for Boolean function. So we will look at properties of cofactors. And we have seen f of xy is equal to fyx. That is, cofactor of f with respect to x is same as cofactor followed by cofactor of fx with respect to y is same as cofactor of f with respect to y first and then x, because they are independent variables. Similarly, cofactor of the complement of the function is actually complement of the cofactor. You can quickly prove that it is straightforward. So the function f can be represented as x fx plus x bar fx bar, and therefore the complement of the function f is given by this, which by De Morgan's theorem you can write in this fashion. And x bar fx, x fx bar into x bar fx bar bar. Now, if I again expand this, you get x bar plus fx bar into x bar bar plus fx bar bar. When you multiply, you get x bar into x is 0. So this into this is 0. This into this is x bar fx bar bar plus x into fx bar. Okay. Then you have this into this fx bar bar. Now this can be represented as x plus x bar into this, because x plus x bar will be 1. So 1 into this is same as this. Now I can club x bar fx bar bar with this cx bar fx bar bar. You can take common term as x bar fx bar bar from this and this. Then you are left with the x bar fx bar bar into 1 plus fx bar. 1 plus fx bar is 1 because it is a Boolean function. So essentially what you are left with is only this and this. Okay. So that is why you get this. So this is the x bar fx bar bar plus x fx bar as the complement of function f in terms of its cofactors. In other words, complement of the function can be represented in terms of the complement of the cofactors like this. Now, suppose if I take the cofactor of this complement function with respect to x is same as taking the complement of this, the cofactor of this with respect to x. Now that gives me this second term, f x bar. So the complement, the cofactor of the complement of the function is same as complement of the cofactor. So that is what this theorem says. Okay. Then these three things we have seen earlier. This is true for any binary operation. Okay. Also note that if so x fx, that is x into the cofactor of f with respect to x is same as x into f. Okay. Any clarification on this? So if f has a term a cube with the x bar as one of the variables, then x into x bar that vanishes. Anyway, that term will not be there in fx. So this is very straightforward case. Let us very quickly see a theorem. Let C be a cube and f is a function. C if C belongs to F, if and only if the cofactor of F with respect to C is 1. So this is if and only if. So if FC is 1, then C belongs to F. Or if C belongs to F, that is, C is a subset of F, then FC is 1. Both these are true. So we have to use the fact that this fact, that is X of X equal to X of F. Now we will quickly see if part. Suppose FC is 1. Okay, FC is 1. What does that mean? FC is 1. Okay, then I can write FC is 1 means F is inside C. Actually, cofactor of F with respect to C is 1. Okay, then CF is equal to C of C, which is equal to C. Okay, because FC is 1. So CF is C. So C is contained in F. Something like this. Only if part, let C is contained in F, then CF is equal to C. If I take the cofactor of this on both sides of this equation, then CF, the cofactor of CF with respect to C, which should be equal to the cofactor of C with respect to C. So this is CCFC. So that is from this. Okay. CCFC, which is equal to 1. Cofactor of C with respect to C is 1. Okay. Cofactor of X with respect to X is 1. So CCFC is 1. So CC is 1. Therefore, FC is 1. So that is the theorem. Very, very simple to prove. Then we will look at what are known as monotone functions. A function f in X is a monotone function if X changes from 0 to 1. X changes from 0 to 1, then if F changes from 0 to 1 or F remains at 0 or at 1, then it is called monotonically increasing function. F is said to be monotonically increasing. What I'm trying to do, we have a function F in which X is a variable. Okay. Now, if X changes from 0 to 1, F also should change from 0 to 1. That is one possibility. Or F remains at 0 or at 1. Okay. So that is called a monotone increasing function. F is said to be monotonically increasing. Same is true for monotonically decreasing function. If X changes from 0 to 1, then if F changes from 1 to 0, or if F remains at 1 or at 0, then it is called monotonically decreasing function. So this is also referred to as negative unit. So the first one is referred to as positive unit, and this is referred to as negative unit. So if F is monotone increasing in X, then F bar will be monotone increasing in X bar. Okay, so that is. Now quickly see this with an example. So F is positive unit in A and C. Why? When suppose B is 1. Okay, suppose B is 1, then B bar will be 0. So this term is 0. B is 1. This term becomes 0. Now, if A changes from 0 to 1, F also changes from 0 to 1. Okay. If A changes from 0 to 1, F also changes from 0 to 1. So therefore, F is monotonically increasing in A. Same is with the C. Suppose B is 0. Suppose B is 0. Then what happens? B bar will be 1. C, let us assume that C is initially we will assume that C is 0. So this term is 0. B is also 0. So when A changes from 0 to 1, F remains at 0 because originally F was 0, B was 0. This term was 0 because C was 0. So F was 0. Now if A changes from 0 to 1, F remains at 0. Okay, so that is one possibility. Secondly, suppose C is 1 and B is 0. So B bar is 1. So F is 1 irrespective of A. So B is 0. So if F changes from 0 to 1, sorry, A changes from 0 to 1, yeah, this F is already 1. So there is no change in F. Okay, value of F. So F will remain either at 0 or 1 depending on other variable values. Okay. So these three possibilities are denoted in this. If X changes from 0 to 1, then if F changes from 0 to 1 or F remains at 0 or at 1, all these three possibilities represent a monotonically increasing function F in X. Okay, so same for monotonically decreasing function, wherein when X changes from 0 to 1, F will either move from 1 to 0 or will remain at 1 or remain at 0. So if you look at that, this is positive or monotonically increasing in A and C. F is binate in B. Binate means it may move from 1 to 0 or 0 to 1 depending on other values, the values of other variables A and C. Suppose A is 1, C is 0. Okay. B changes from 1 to 0. Okay. B changes from 1 to 0. A is 1. B is 1. So F is 1. Now B changes from 1 to 0. Then what happens? This becomes 0. So F changes from 1 to 0. Okay. On the other hand, if A is 0 and C is 1, now B changes from 1 to 0. Then what happens? Initially, F was 0 because A was 0 and B is 1, C is 1, but B bar was 0. So initially F was 0. Now B changes from 1 to 0. Then B bar changes from 0 to 1. So F changes from 0 to 1. So you can't say whether F is monotonically, actually F is, increasing or decreasing depending on the value of other variables when B changes. Therefore, F is referred to as binate in B. It is not unate. So as a whole, F is a binate function because it is not unate in all variables. So on the other hand, if you look at this function, F is positive unate in A and B. That is monotonically increasing in A and B, whereas it is negative unate or monotonically decreasing in C. So this is very easy to see. Suppose A and B are, these are 0, any one of them is 0, then F becomes C bar. When C is 0, F is 1. When C changes from 0 to 1, F changes from 1 to 0. Okay, so that therefore it is negative unate or monotonically decreasing function. Any queries so far?
No, sir, it's clear.
So if a function is unate in all its variables, then the function is said to be unate. Okay. So if F is positive unate in X, what does that mean? You don't have a term X bar appearing in F. Okay. So F is positive unate in X, then Fx contains Fx bar. Right? fx contains fx bar, because f is positive unit. That means f has a few cubes in which x appears in the uncomplemented form, or it does not appear at all. Okay. So when you take the cofactor of f with respect to x, then you get fx. That means it gives you all the cubes of f with the x set to 1. So that is fx. But if I take the cofactor of f with respect to x bar, those cubes which has x as a variable will be set to 0, whereas those cubes which do not contain x at all are assigned to this fx bar. So if you look at overall, fx will be bigger than fx bar. Okay, probably we have an example. Okay, we can see an example. Okay. Suppose I have same function. Okay. F is equal to AB
Sir, the presentation stopped.
Are you able to see now?
Yes, sir.
Okay. So suppose we have this f is equal to AB plus C bar. Okay. So now, if what is FA? Can we quickly see? Tell me. FA is what?
B plus C bar.
B plus. What is FA bar?
Only C bar.
C bar.
C bar. So FA contains FA bar. Okay, because when you say A bar, that is the cofactor of f with respect, you get terms only which are not dependent on A. Okay, and this is positive unit in A. Okay, so if f is positive unit in X, then fx will contain fx bar. So this is one example. Is that fine?
Yes, sir.
Okay. So there are other. So this is our example for actually this. Okay, so this is example for this. So you can also prove that using this if f is positive unit in X, then I can write f as x fx plus x bar fx bar. Since it is positive unit in x bar doesn't appear at all. Okay, so x bar is not there at all. So I can write it as x fx plus fx bar. Okay, now if I take the cofactor of f with respect to x, you get f of x. Here you get this fx. This is fx. Whereas this boils down to fx plus fx bar, because x is set to 1. Now fx is fx plus fx bar, which implies fx contains fx bar. Okay, so that is how you prove it is positive unit in x. If this holds good, then x is positive unit in, sorry, f is positive unit in x. Okay. So similarly, the cofactor of f with respect to x bar will be fx bar. Now let us consider the other possibilities. F is x fx plus x bar fx bar, and which if f is positive unit in x, then I can represent that in this the second term this way. Now I take the complement of this with respect the complement of this function f, which is nothing but the complement of this, which using De Morgan's theorem, I can write in this fashion, which is x bar plus fx bar into fx bar bar. When you multiply, you get fx bar bar plus the product of these two. Okay. Now this is x bar fx bar plus this, you see, f x bar into fx bar bar. Now since you see fx is contained, fx contains fx bar, which means fx bar is small compared to fx. The complement of this will be bigger than the complement of this. Do you agree? The complement of fx, it is something like this. Okay. So you have this. This is, let us say, f. Okay. This is our whole universal set. Okay, I denote it as u. What is u? If f has two variables, u is in both the variables, the function u is 1. In all, whatever the value the variables take, the function is 1. So that is u. Whereas f is a Boolean function, which is true only for a certain values of the variables. See, suppose f is equal to ab, it is 1 when a is equal to 1 and b is equal to 1. Whereas u is 1 for all values of a and b. Obviously, f is a subset of this u. Okay, universal set. So what is f bar? This is f bar. Okay, this is f bar. Okay, so this is f bar. So f union f bar is our universal set. Okay, when you add these two, you get the whole. Now you take the cofactor of f with respect to x. That will be even smaller. Okay, a smaller set. So if I were to do that, it will be something like this. So you have this. This is my f, and maybe this is fx, and this may be fx bar. Another remaining thing. Maybe. Okay, it may have overlapping also. Okay. Now, in our case, in the present case, see, when f is monotonically increasing, f is monotonically increasing x, then this will be, this will be fx bar. Fx bar will be smaller, whereas this this whole thing will be maybe fx, because fx contains fx bar. Now, when you take the complement of fx bar, that will be everything except this portion. Everything except this portion. So that is bigger. Whereas complement of fx will be only this outside portion. So that is smaller. So fx, therefore, is contained in fx bar part. Okay. So therefore, this boils down to fx bar. Okay. So that is why we have this expression, that is f bar is x bar fx bar plus x bar fx bar bar plus fx bar. Okay. So for a negative unit function, f is fx plus x bar fx bar, but f bar will be x fx bar plus fx bar bar. Okay, this is for negative unit function. Okay, so you can try some examples and see whether you get the same answer. Okay, if you have any questions, please go ahead.
Sir, I have a question.
Yes.
Sir, there's a statement written in the slide above. It says if a function is unit in all its variables, then the function.
This one.
Yeah, this one. Yeah. So here, if a function is unit, by that you mean that it should either be positive unit or in all its variables, or negative unit in all its variables, right?
No, it is not like that. A function can be, let us say a function has say n variables.
Okay.
Yeah. Now the function is positive unit in some variables and negative unit in some other variables.
Okay.
Suppose f is equal to, I will use the same ab plus c bar. Okay, f is positive unit in a comma b and negative unit in C. Okay. So f is unit in all the three in these all the variables. In some variables it is positive unit, whereas in some other variables it is negative unit. But overall the function is unit.
Yes.
That is what I mean by this. This sentence means that not necessarily it should be unit only positive unit in all variables.
Okay, but sir, suppose if a and b is 0 and c goes from 0 to 1.
Yes.
Then f goes
from 1 to 0.
Yes.
It is a positive. It is a negative unit. That is what is meant by negative unit. That's what this whole. That is the meaning of when x changes from 0 to 1. Now c here x is replaced by c in our example. When c changes from 0 to 1, f changes from 1 to 0. Here.
Okay.
So it is a negative unit function.
Okay, so but if c is 1 and a b,
the moment c is 1, so this whole term becomes 0.
Yes.
Okay. Now you tell me.
So now if say a and b go from 0 to 1, then
both of them, or one, anyone.
Both of them. Otherwise, it still remains. Okay, yeah, anyone.
See, suppose c is 1, so c bar is 0. Okay.
Yes.
And b is also 1. B is 1. Let us say b is 1, c is 1. So this is 0. B is 1. A changes from 0 to 1.
Yes.
Okay. Then what happens? F changes from 0 to 1.
Yes. So then it's positive unit.
Yes, that's what. F is positive unit in A and B. Here, that is what I mean by this. F is positive unit in A and B.
Okay.
Okay.
Yes, sir. I got it. I got confused. I thought like when you said when unit is mentioned, I thought it's like either increasing or decreasing, not both.
No. You consider this scenario. You consider this following scenario. C is 1.
Yes.
And B is 0.
Okay.
then what is f? Let us think of a changing from 0 to 1. B is 1, B is 0. Okay.
Yes.
Then it's 0.
Yes.
Now, even if a changes from 1 to 0 to 1,
It'll still be 0.
it will be 0. That is why this second, when x changes from 0 to 1, f changes from 0 to 1, or f remains at 0 or at 1.
Okay.
These two together tells us whether it is monotonically increasing or not. Even if it remains same, it remains at the same value 0 or 1 because of other variables.
Okay.
Okay.
Yes.
So on the other hand, if C is 0 and B is, so C is 0 means it is already 1.
Yes.
Whether A changes from 1 to 0 or 0 to 1,
It'll
has
still be
no
1.
effect on this. So F
Yes.
remains at 1, even if A changes from 0 to 1.
Okay.
So that is this F remains at 1. Okay.
Okay. Sir. Yes, sir. Got it.
Any other question? No. Why do we need to look at this? See, one very quick this thing is, if the function is unit, okay, let us assume that it is positive unit in some variable, yes. Then fx contains the fx bar, right? Are you with me?
Yes. Yes.
Yeah. So now we in the two-level minimization, we will be looking at whether a function is universal function. What I mean by universal, that is this. For all variable, whatever the variable value, the function may assume may be 1, irrespective of what value a variable takes. Okay. Suppose we see the example again, I would say something like this. Okay. Suppose I have f is equal to a b plus a bar plus b bar plus a bar b bar. Okay, something like this. This is function variable a, b, 0, 1, 0, 1. So ab is this term means this. A bar is this. B bar is this. Okay. So even a bar, b bar is not required. Let me remove that. Right. Now
Yes.
this f is actually a universal function, isn't it? Because for whatever value a and b takes, the function value is 1. Right.
Yes. Yes.
But when you have thousands of variables, you will never know whether f is a universal function or it is not a universal function, isn't it? By just looking at the cubes, you can't say. Do you get my point?
Yes, sir.
Okay, so when you have hundreds of variables, by just looking at the function, you can't say. But now, suppose I somehow find whether it is a universal function. Okay, now you extend this to this. Suppose if f is a unit function, okay, in x, positive unit function in x, then I know that fx contains fx bar, and if fx bar is universal function. Okay.
Okay.
Suppose fx bar is a universal function, that is irrespective of what value x take, this other variables take, it is 1. Then I can straight away say fx bar is universal function, which implies fx is also universal since fx contains fx bar. Do you agree?
Yes.
Yeah. So we will be reducing some computation of finding whether fx is a unit function. Sorry, fx is a universal function. If fx bar is a universal function and f is positive unit in x. So I need not compute this at all. I can straight away say that fx is a universal function just by looking this. Okay, so there are some optimizations that we can do while doing the 2-level minimization, multi-level minimization, and so on. So these things will be applied there. Okay.
Okay.
Yeah. Any other question? Okay, if there are no other questions, we will meet day after tomorrow, Friday. Okay.